selecting the right patients for refractive surgery, and how to diagnose glaucoma and treat it using these advanced tools, and also how you can use these tools for specialty lenses in keratoconus. So without further ado, I would start with the first talk. I have two great speakers with me, Dr. Gadi from Italy and Dr. Fu from, from Ho Chi Minh City. Okay, so let's talk about how we can enhance the pre-refractive diagnostic screening with Pentacam and Corvis ST. I have no financial disclosures to make. So just for introduction, what exactly is corneal biomechanics? Biomechanics is basically the branch of ophthalmology that studies the biomechanical properties of the cornea. We all know that cornea exhibits both viscoelastic, that is elastic, as well as viscous properties, and due to this property of the cornea, it also has corneal hysteresis, which is nothing but the ability of the cornea to dissipate, absorb, as well as dissipate energy during a bidirectional applanation process. So this is a dynamic behavior of the cornea that is not a constant measurement. So why study corneal biomechanics? Now the understanding of corneal biomechanics has been an area of intensive research in the last decade, and why this was thought to be important was because many times patients who had good topography and good corneal thickness also went into ectasia, and these are those cases where we don't know why this happens. So probably corneal biomechanics could help us in understanding this very ambiguous phenomenon of ectasia development. So most of the times it was found that there was a faulty preoperative refractive screening that was involved, and this also is important for diagnosis, management, and follow-up of keratoconus patients, which definitely a refractive surgeon should also know and understand. Diagnosis of glaucoma will be taken by other speakers. So it is known that the progression of keratoconus doesn't happen in one day. Okay, so you have biomechanical keratoconus that actually precedes the stage of topographic keratoconus. Okay, so you have first a normal cornea or a healthy cornea to begin with. Then there are changes in the elasticity of the cornea. Then comes the stage of biomechanical keratoconus. Then tomographic keratoconus, where it can be seen on the posterior surface. And then topographic keratoconus, where you can actually diagnose it on the anterior surface. And finally, the stage of manifest slit clamp findings, where you can actually see all these advanced changes, but it is too late by then. So with the biomechanics, the study of biomechanics and using Corvis ST or similar equipments, you can actually catch the disease at the biomechanical keratoconus stage and prevent it from further progression, or you can treat it well in time and rule out these patients for refractive surgery. So this is the current standard of refractive surgery care pretty much in most of the institutes. The patient comes to you, you do a complete eye examination, and if you just have a corneal topography, then what happens is you diagnose it either as abnormal or suspect or normal. If it's normal, patient can undergo LASIK, SMILE, or whatever corneal refractive surgery you prefer. And if it's abnormal or suspect, then of course you either do cross-linking, or depending upon the refraction or the degree of suspicion, you can choose a different modality such as surface ablation or phakic IOLs, or you can do extra procedures. Now in the normal category, what happens is if you have okay, so if you've done your LASIK or SMILE, whatever, but you do not know whether the cornea was biomechanically a weaker cornea or it was a normal cornea, because you did not do biomechanics. Now, a biomechanically weaker cornea has a higher risk of going into a post-refractive surgery ectasia, whereas a normal cornea is expected to remain uneventful. Now, how the scope increases with corneal biomechanics in refractive surgery. So along with corneal topography, if you add biomechanics, then you have now three categories. You have a patient who has abnormal topography as well as abnormal biomechanics. Now this will directly go into a C3R category. I mean, it's a keratoconus obviously, and you'll have to do a C3R. You can have a situation wherein the topography is normal, but the biomechanics is abnormal. Now, in these cases, you have to be very cautious. You can plan to choose a surface ablation procedure, which is much tissue saving as well as thought to be safe in those suspicious corneas. And if the power is higher on the higher side, then you can go for an ICL or a PK covered surgery, or you can combine a cross-linking. However, if everything is normal, then of course there is no risk, and patients can you can treat these patients confidently with LASIK or SMILE. Now, just briefly, how to measure corneal biomechanics. There were ex vivo destructive testing techniques which involved strip extensiometry and pressure invasion of intact corneas, and in vivo non-destructive techniques such as ORA, Corneal ST, Brion microscopy, etc. So I will be discussing about Corneal ST in today's talk. So Corneal ST essentially is corneal visualization Scheinflug technology. It is based on the principle of air pulse tonometer. It's essentially a combination of air pulse tonometer with a high speed Scheinflug camera that tracks the biomechanical response of the cornea in response to the air pulse. So you have an air pulse, and then the cornea deforms, and the Scheinflug camera tracks its movement. So within 31 milliseconds, the camera records 140 images of the horizontal sectional plane with a frame rate of more than 4300 images per second. So this is how it happens. And basically what you are seeing here is, at the beginning the cornea is in its original initial convex stage. Then the air pulse drives the cornea backwards until the first applanation occurs. Afterward, the cornea is further deformed until the moment of maximal concavity, and then you also have a oscillation phase where the cornea returns back to its original shape, and before it reaches the original shape, it also passes through a second applanation where the cornea is flat again. So these are basically the stages of deformation that the Scheinflug camera records. Now, if you see deformation response in various conditions, so this is the normal cornea. Okay, so the air pulse comes and it deforms the cornea. So this is the stage of maximum concavity, and then there's a little bit of oscillation. This is normal response. Now here on top you have a keratoconus cornea. You can see the deformation is much more compared to a normal cornea. So you can compare and then diagnose keratoconus. On the other side you have a keratoglobus where you can see deformation is very clear. Even you don't even need something to compare. It is so thin and so such a weak cornea that it deforms and oscillates much more compared to keratoconus. And you can also use it to check the corneal stability post cross-linking. So you can see the lower one is the cornea which is cross-linked, and the deformation comparatively is lesser. So it shows a stiffer cornea post cross-linking. So you have the DCR display, which is dynamic corneal response. You have various parameters here. You really don't have to remember each and every parameter and its normal ranges and all. Most important is the deformation amplitude. So deformation amplitude essentially, if it is high, it means the cornea is deforming much more. So it indicates a weaker cornea. And there are lots of other parameters: length, velocity at applanation 1 and 2, highest concavity, and BIOP. So what is BIOP? BIOP is very important. How it is different from GAT corrected or corneal thickness corrected IOP is because it takes into consideration the corneal thickness, age, as well as the biomechanical properties of the cornea, thus enabling an accurate IOP estimation. So the IOP estimation, especially in those cases where the biomechanics has been altered, such as post-refractive surgery, will be better estimated using the BIOP. So where I see the practical use of BIOP is our post-LASIK or post-SMILE patients, and post-op when you see their IOP is say 18 or 17, you think that it is normal, but actually it could be an early steroid response. So if you just do your NCT. So this is where BIOP is much more useful because you should see a change, but it should be slightly less. But with NCT, it can be, it will not be very accurate. So you will probably miss those early cases of steroid response. And we have seen certain cases where we actually diagnosed the early response using the BIOP, and we stopped the steroids or tapered them more quickly. So this parameter was proven and shown to have accuracy, and especially after refractive surgery, it is much more accurate than conventional methods of IOP. Now there is a screening report called the Vincigora screening report that displays the normal ranges of DCR parameters as a function of BIOP. So there are three parameters that are more important for you to know: a stress strain index, stiffness parameter SPA1, these are newly added parameters, and the CBI, which is the Corneal Biomechanical Index. Now just briefly about this, CBI essentially was developed by Riccardo and Vincigora from Italy in order to detect early keratoconus based on biomechanical response of the cornea. Now it is derived using a logistic regression formula that includes the regular DCR parameters as well as a stiffness parameter. Now many of these cases could be detected just by CBI, even though there was no topographic evidence of the disease. And a value of more than 0.5 is generally considered to be significant. So the second parameter is the stress strain curve. So CBI you can see here on the right lower side. Stress strain curves and index is another new parameter. So it essentially describes the intrinsic elastic properties of the cornea. And what happens is, if these curves are shifted to the right, if you see here, the cornea is generally softer, and if they are shifted to the left, the cornea is stiffer. And SSI or stress strain index describes the position of the curve. 1 indicates average or normal elasticity of a healthy corneal tissue, less than 1 a softer behavior, and more than 1 a stiffer behavior than the normal. The next parameter is the stiffness parameter SPA1. This was found to be most closely related to the corneal properties and was proven to be clinically useful in screening of keratoconus with the highest sensitivity and specificity compared to other parameters. And along with the DCR parameters, it can be used to biomechanically characterize eyes with specific pathologies. Now here, if you see how the behavior of a soft cornea would be compared to a stiff cornea. So on the top, if you see, it's a soft cornea. The DA ratio, the integrated radius, the ART and the SPA1, all these parameters are lower, they are lesser. Basically the DA ratio will be high, integrated will be high, and the ART and SPA1 will be lower, and the opposite happens if it's a stiffer cornea. It also gives you a comparison display wherein you can see the changes in these parameters post cross-linking in a keratoconus patient. Okay, it also has a best display, which is important for monitoring of the biomechanical changes over time, and especially to verify the success of treatment after cross-linking. It can also be used for post-NPCI cases. Now, recently what has happened is the Pentacam has been integrated with the Corvis ST, and this integration is shown as the ARB display. So it has the CBI and the BAD-D, CBI from the Corvis, the BAD-D from the Pentacam, and it actually gives us a value of TBI. It calculates TBI, which is the tomographic biomechanical index combining both. The cutoff of TBI is 0.3. Anything more than 0.3 would denote a suspicious cornea. Let us look at some of the cases where this integration helped us to do a better refractive surgery planning. So this is case 1 of a 21-year-old male. He had moderate amount of keratoconus, moderate amount of refractive error, myopia and myopic astigmatism in right and the left eye respectively. So if you see the quad map and the BAD maps look pretty normal. The Vincigora screening report, the stiffness parameters 1.28 is okay, but if you see the CBI is on the higher side. 0.79, it's showing in the red zone. So it's color coded and easy to understand actually. For anyone, you really don't have to learn or remember all the figures and the cutoffs. So you can see it's 0.78. BAT is within the normal range. TBI is also within the normal range. So what do you do in these cases? Now, what it shows is that topographically patient's cornea is normal, but biomechanically it's a weaker cornea. So you cannot really, do your SMILE or LASIK with 100% confidence, because as I said, these are those cases which we want to detect, which can go in for ectasia later on, even though having a normal topography. So this is a similar kind of situation in the left eye also for the patient. So what we planned for this patient was SMILE extra, because of the high CBI. Okay, so patient has high CBI, borderline TBI in one eye. So this was the first eye. Okay, the right eye, high CBI value, normal TBI. Okay, so some people ask me, okay, if the TBI is normal, then everything should be normal. It's not the case, because it's just the combination of both, but you cannot ignore the CBI. So if the CBI is on the higher side, then you also have to be cautious. So high CBI, normal TBI, moderate to low myopia, RST was good, but we still combined it with cross-linking. And the other eye also had the similar treatment. Case 2 is of a 31-year-old female, low myopia in both the eyes. Bad maps look normal. And if you look at the CBI here, is again high. TBI is again normal. But since the myopia was on the lower side, we still wanted to be more conservative and treated the patient with PRK procedure. So in the similar way, the other eye also showed same parameters. High CBI, normal TBI, low myopia. You can either do SMILE or PRK, but PRK I think would be better because it preserves more tissue. So this is how it helped us in selecting a proper procedure. So case 3, again 22-year-old male, moderate myopia in both the eyes. So there are few changes. If you see in the BAT display, the final D value is on the higher side, and the ARV display, you see the CBI is again high, 0.87. BAT D is also in the yellow zone, 2.23, which is higher than normal. TBI is also in the suspicious. So I said TBI cutoff is 0.3, so it is 0.52. Now you have a situation where your CBI and TBI both are kind of abnormal. So you would probably not want to do any corneal refractive procedure in these cases. Okay, so just go ahead. Either you watch the patient for development of keratoconus if the patient is not in a hurry to get refractive surgery done. You can always observe these patients over time, or else you see stability for 6 months or 1 year and then plan a CAKE IOL. This was what was done for this patient. Now, COVIS also gives us something known as CBI LVC. So there was nothing till now that could actually tell us about the risk of ectasia after refractive surgery. So this particular software or tool allows an automatic assessment of the biomechanical stability post-operatively, and was developed to differentiate between stable eyes post laser vision correction versus those that could develop ectasia. So this is a display, and here is the CBI LVC. So value of 0.5 or more again is suspicious. So to conclude, I think Cordis and Pentacam integration, it serves as an indispensable tool in screening patients for refractive surgery, which is highly important these days. You just cannot treat any patient who comes to your clinic and wants refractive surgery, because there are lots of issues there, medical legal issues, and otherwise also you don't want any ectasias. So it helps us in selecting appropriate procedure, either a LVC or an extra procedure or a CAKE IOL. It also helps us to monitor biomechanical stability of cornea after LVC, as I said, with the LVC CBI tool. And also it's very important to monitor progression and verify success in keratoconus patients post C3R. So these are all the basically practical uses of these tools that we are in Netralhamai Hospital using since we had this integration of cornea, the Cordis and the Pentacam, and we find it very, very useful in our practice. Thank you so much for your attention.
So yes, I will be talking about the specialty contact lenses, especially scleral lenses, and how to customize scleral lenses with the. Okay, so why did I want technology in my practice? Technology, I wanted technology because I design all my rigid contact lenses, scleral lenses, ortho-K lenses, and corneal lenses. So to customize contact lenses, to get to the next level, to customize not only the posterior surface of the lenses, but we can customize also the anterior surface of all these lenses to save time when designing lenses. It's easier, automatic, and more accurate for the calculations. And it will reduce the lens applied on the eye, the lens ordered, and it will reduce also chair time. To manage complex cases, because technology will not allow us to only customize the lenses, but to monitor the corneal health, and we will see an example of this, a case, and to include fenestration channels microvolt. We will see how to do that, because patients ask for technology. And I use technology to educate patients how to do that. So I design their lenses and I tell them how I design these lenses. When they see these designs, they feel very special, and I explain every step in the designing and why I did that curve instead of another one. So let's start to see how important is the technology. The back surface of the scleral lens is crucial to align with the conjunctival tissue, with the sclera underlying the conjunctival tissue. When you are fitting corneal lenses, you are fitting the lenses, they are aligning on the cornea. The corneal lenses align and touch the cornea. So you have to understand the corneal topography to best understand what design do you want to do for that eye. With scleral lenses, we need to know what is happening in the sclera. That's why it's very important to understand what's going on to allow better alignment, and better alignment will provide better centration, better visual acuity, and better comfort. And all these factors will allow us to avoid complications and dropout. Why it's important to understand what is going on the sclera, what shape is the sclera. This amazing study in 2017 by the Grantinier and al. Found that almost all scleras, about 67% of scleras are asymmetrical or taric. This means that they are or irregular, or less than 6% of scleras are spherical. So if you are fitting spherical scleral lenses, you will have less than 6% of success of the fitting, because most of these scleras are asymmetric. More than 40% are asymmetric. How to understand what asymmetry? When I'm talking about asymmetry, I'm talking about quadrant-specific design. So the sclera has a different shape in the different quadrants designs, okay, and then different quadrants of the sclera. I told you because patients ask for them. So I receive messages from patients from all around the world asking me, not asking me if I fit scleral lenses, they ask me what technology I use when designing these lenses. They know all the technologies, and they ask me if I have that exact technology they are searching for. So now all patients are very open, very educated, and they know what they want. This is a few days ago. Patients from Germany, patients from Malta, they wanted customized scleral lenses. They didn't ask for scleral lenses, they want them customized. Customization is very important, not only for the comfort. We know that visual acuity is crucial to avoid dropout, so we need to allow a better visual quality for these patients, especially in keratoconus, in post-keratoplasty, and post-refractive surgery, because they have high-order aberrations. And there are so many ways to correct these high-order aberrations with scleral lenses, because the scleral lens is large, is stable, so we can add this technology to the anterior surface. What technology we can add? Tonicity, multifocal optics, prism, eccentricity, and high order aberrations correction. So this is an old study who showed that switching only from spherical to toric lenses, this increased overall satisfaction, comfort, and wearing time. So only by switching from spherical to toric, not quadrant-specific design, to toric, this had a great impact on patient experience. And also we increase empathy. We need to understand what our patients want, what they are asking for, and we need to meet their expectations as well. There are so many technologies available now to detect and to map the sclera. And we have the Pentagon CSP. I use this device and plus another software we will see later to design and customize all my scleral and ortho-K lenses and also corneal lenses. So the Pentagon will map the sclera up to 18 millimeter. It will give you the corneal and scleral topography in one shot. The new software will be in one shot, but only one topography. You will have an overall view of the ocular surface up to 18 millimeter. So here the software will provide you all the information, the ocular sagittal height at a certain point that you will give it depending on the lens diameter that you have in your diagnostic set. It will give you also the amount of toricity between the two main meridians, and you can use all this information to have to start the fitting from a diagnostic set. How to do that? So to understand, the first steps in selecting the first lens from the diagnostic set are the total diameter, the first one, the second one, the lens sagittal height. So how to understand the lens sagittal height? Here the software will help you. You need to put the initial clearance that you want to have for that lens, and the software will calculate for you the lens sagittal height at that point that you have put here. So you will directly have it without doing any calculation by yourself. You go to the diagnostic set, you pick that lens, and you apply it on the eye. And it will be only one lens applied on the eye, not several ones to get the best volt, the best clearance. So you can use that software to select a lens from diagnostic set, but also you can use it to have a customized lens. So this is software that I was telling you before. You have to go and to select the external software. It's online software, so this is the first step. The second step, the software needs to understand the power of the lens. So first of all, you need to include the refraction. You can include the refraction, or you can include any scleral lens that you have in your practice. So you put it on the eye and you do the over refraction. And you need to include all this information: the base curve, the power of the lens, and the over refraction. Then the third step is to determine the lens diameter that you would like to have. So you decide the lens diameter and the volt of the scleral lens. Okay, initial volt should be about 350 at least, because a scleral lens will settle on the eye, and this volt will reduce. Then the fourth step, you will not do anything. That software will do anything for you. So the software will design a lens that you can send to order to the lab. So here is the fluid reservoir profile. You can see how the fluid reservoir is downside behind the lens. You have a highly customized lens. So here you can see how these, I don't know if you can read them, I don't think so, but you can see how in every semi-quadrant the lens sagittal height is different. You know, when you customize a scleral lens, generally you customize the lens periphery. With this software, you are customizing all the lens. Only the optic zone will be spherical. So the customization will start from the corneal area, limbal area, and to the peripheral area. So you have a highly customized lens from the corneal area to the scleral area in a semi-quadrant design. So this is the first case of keratoconus. This case is just to show you how important it is to have technology, not only to design the lenses, but to understand what is going on also to the cornea, to the corneal heads. So this is the keratoconic patients with advanced keratoconus at lens delivery. The visual acuity was very high. Here you can see the topography. And at 1 week follow-up, he had a very reduced visual acuity and he had a hyperechoic shift. When I removed the lens, I saw staining the eye. I saw staining in the corneal area and the limbal area. And this means that the lens was frictioning on the limbal area. Frictioning on the limbal area will cause edema. So this frictioning has caused edema, and the edema has caused hyperechoic shift. So this was my intuition. What I did next is to perform a pachymetry. And indeed, this is the pachymetry after lens removal, and this is the baseline. And indeed, the patients have developed edema, more than 4% of edema. And this have caused the hyperechoic shift. So what I did to this design, and this very important to educate the patients what is going on with the lens and the lens on the eye. So from this design, what I decided to do is to increase the clearance in the corneal area and the limbal area. You see here how the limbal area, limbal volt increased, and also the peripheral volt of the corneal area. You see here, you can see it now. So I increased the volt in the peripheral corneal area and also the limbal area. And this new design have resolved the edema. So changes, you can do changes in central clearance, limbal area, and the alignment. You can do all the lens, or you can do half the lens. So when you have the half lens, you need to indicate which half lens you want to modify. And you can do the modification in only one quadrant. So it will not be all the quadrant. The changes that you will be doing is only in this dark green. This meridian, the 0 and 90 degree meridian, will not be affected by this change. So it's very highly customized modification and design. So customization is very important when you have pinguecula. Who fit scleral lenses knows how pinguecula are frustrating for you and for the patients. Not easy to manage this particularity of the eye. When you are fitting a scleral lens, a normal diameter scleral lens, the pinguecula will lift the lens up of the ocular surface. The breeze will enter inside and the patients will experience discomfort. You can fit a larger lens with slight compression, which is okay, but the lens will be frictioning over the pinguecula, and this will cause inflammation to the pinguecula. So it's not a very good option. What we can do is to include a volt over the pinguecula, so the lens will volt over the pinguecula. You can order this to the lab if they are available, or you can do it by yourself with this software. So here is alignment of the lens in the overall view, the two meridians, so the two opposite quadrants, and here you can have a better view with a magnification of that area. So this is the lens without any microvolt, and we will see how this has changed by including the little elevation of the in the periphery 2 volt over the pinguecula and the conjunctival tissue. So here you can see it here, and you have also all the information of how much is high this volt over the conjunctiva, and understand if you need it higher or lower. So this is a video, I don't think. Yes, so you can see here by rotating here the white line, you will see how this elevation is included only in one quadrant where the pinguicular were included, while in the other quadrant there is no need to include, and there was no changes in the lens design, in the lens build. So here we have corneal irregularities, because irregularities we can have them in the conjunctival tissue, but also in the corneal area, especially in Salzmann's disease like this. So we need to have this microvolve in the corneal area, and obviously you can do it with the software, including this microvolve in the corneal area. So here you can see it not anymore in the scleral area, but in the corneal area. And here again, you can move it and see how this microvolve is included only in one quadrant where you decided to include it. So when fitting scleral lenses, we have so many issues caused by an oval limbus. We all have oval limbus, but when you are fitting a spherical lens on a significant oval limbus, the lens will land near to the limbus in the horizontal meridian and far from the limbus in the vertical meridian. This will create excessive clearance, and excessive clearance inferiorly cause so many problems. So what to do here? You need to reduce the fold, but if you reduce the fold vertically, you will be touching the horizontal meridian, and this will cause edema, frictioning, so staining, epithelial villi, and edema. How to do this? You need to design an elliptical lens. I've been talking about oval lenses since 2017, and now finally some labs have included this technology in the diagnostic set. So elliptical lenses are designed based on the HVID and VVID. This is the article where there are two possible designs for the elliptical scleral lens. So here in this article, I explain how to do this. With this software, you can have oval lenses. So you need in the vertical, in the horizontal meridian, it's not well seen here. So in the horizontal meridian, the vault over the limbus is larger, and in the vertical meridian, the vault is smaller. So large, small, you have an oval lens. Anterior surface, very important to customize as well. What we can do, as we said before, you can add toricity. So by adding here in the modification area, you can add the cylinder, and also need to understand where the lens is rotating, so the software will compensate the rotation exactly as we do with soft contact lenses. We can add multifocal optics as well. So what you need to add, only the addition for near vision, the pupil area, which is the multifocal zone. You can increase it, you can decrease it as you want, and you have to design the center distant and center near. So depending on the patient's needs, you can understand what designs you want to do. Here you are seeing the curvature front, so you see how the profile of the anterior surface of the lens is changing as well. So when you are adding some customization, the anterior surface, like multifocal lenses and correction of high order aberration, the lens should be very stable on the eye, not decentered, because if the lens is decentered, you will create vertical coma, and this coma, high order aberrations, will worsen the visual quality of the patients. However, in some patients, it's very, very difficult to obtain a well-centered lens. So what to do in these cases? There is a technology that can decenter the optic of the lens. So the lens will stay decentered, but the optic zone of the lens can be decentered. So you can add all the technology that you want on the anterior surface. So this is another case of a regular cornea. He wanted a good vision, and he wanted a good far distance and near distance vision. So he tried soft contact lenses, but he wasn't happy with the vision because it was unstable. So what I did is map the corneal and scleral profile and design a lens for him. So this is a lens very well aligned, no conjunctival blanching, no indentation, and the vision was very stable. He was very happy. This is another patient from Germany. So she was desperate because she was wearing the corneal lenses, but she was experiencing a lot of discomfort. So here again, she had keratoconus. So she had a little bit of discomfort because the keratoconus was advanced and the corneal lenses were not stable on the eye. So I designed the lenses also for her, and she was very happy. So here, this is for a high order aberration profile, a LASIK patient. After LASIK, you have high order aberration, so you can have a lot of halos, starburst, and bad vision during night. So what it's important to do here in these cases is to register the high order aberration, the baseline one, and to compare them with the ones that you will measure over a scleral lens. So what I did is to fit her with scleral lens with standard optics, because generally scleral lenses will correct some amount of high order aberrations. So she had good results, but the trefoil was increased. So she was complaining still about high order aberration. The next step in this case is to include the front surface eccentricity. I decided 0.6. So here you can see a little bit of decentration of the lens. And when you are adding front surface eccentricity and the lens is decentered, you will increase coma and you will increase high order aberration. So indeed, she wasn't happy with the front surface eccentricity. So in this case, what you need to do is to add a wavefront guided technology to the scleral lens. It's a technology that you can add to the anterior surface, and it will correct the whole aberration of the eye. But to correct the whole aberration of the eye, not only to the cornea, you have to measure them. So here the measurements are with pentagon, the Zernick polynomial, and also you have the E visual acuity, so you can understand these high order aberration from where they are coming, from the cornea or from the internal optics. So here, after fitting a customized lens, you have the baseline and you have also the result with the wavefront guided scleral lens. So when we have a patient very happy, we are also very happy. With customization is very important, not only in simple cases, but also in complex cases. You saw a simple case of multifocal lens, so you had a patient satisfaction only by adding multifocal lenses. And it's important also to understand not only to design a well-aligned lens, but we need to also to monitor corneal health. We need to maintain corneal health with lenses. And when you are monitoring and understanding if the corneal response is okay, what you are providing, not only customized lenses, but a customized care. Thank you.
Thank you, Dr. Kabu, for that very excellent speaker, Dr. Folk, who is the lecturer in Ho Chi Minh's Medical University at Chore Hospital, and he'll be speaking about corneal biomechanics in glaucoma.
Thank you for your kind introduction. I'm very happy to be here to sharing my knowledge about corneal biomechanics in local management. This is my financial disclosure. We know that glaucoma is an optic neuropathy characterized by the progressive loss of retinal ganglion cells and their essence. And high intraocular pressures is a strong risk factor for glaucoma. But we also know that about 1/2 of untreated glaucoma patients have not high intraocular pressure. This is the human lamina gravosum with many pores that the essence pass through it. When the intraocular pressure is high, we see that the lamina gravosum is posteriorly bowed and compressed. And that phenomenon promotes the damage of axon and their cell body, and also affects the diffusion of nutrient from capillary to the axons. And finally, the patient lost their retinal nerve fiber layer. This is a very important index, lamina gravosum curve index LCCI. We can see the yellow lines is the distance from the breast membrane opening from both sides. and D is the distance from the yellow line to the surface of the lamina granulosa, and the LCCI is calculated by this formula. Now we see in the A, B, C is the picture of the normal person. We see that the distance from the yellow line to the red line is the above. And the D, E, F is the picture of a high pressure glaucoma. And we see a significant difference in LCCI is high pressure glaucoma and a normal person. How about the LCCI in normal tension glaucoma? And this is a very interesting study. They compare the LCCI in one eye with normal tension glaucoma with the other eye of the same patient. And this is the result. We see that the LCCI is normal tension glaucoma is higher than the healthy eye in the same patient. So the high pressure is not the only factor that affects the formation of the lamina granulosa. This is the CNTCS study, one of the famous study of glaucoma in the 21st century, and they also show that in the patient with normal tension glaucoma, they will get benefit from lowering the pressure 30%. So the deformation of lamina granulosa is not only affected by the high pressure, but also the relation between the pressure and the stiffness of the lamina granulosa. If we have a patient with a high pressure, we reduce the pressure and may not be care much about the stiffness. But if we have a relatively normal pressure and a clear evidence of glaucoma damage, we must concern about the stiffness of lamina granulosa. If the patient have a strong lamina granulosa, we just need to follow up. But if they have a soft lamina granulosa, we need to reduce immediately. So in clinical practice, we need to know two important factors. First, what is the true intraocular pressure? What is the exact pressure inside the ocular? And the second question is, if we have a true IOP, how to measure the lamina granulosa stiffness? That is the ability of lamina granulosa to suffer from the pressure of the patient. First, I talk about intraocular pressure. We know that intraocular pressure is the most important factor in glaucoma management. We use this for screening, for diagnosis, for set up the target IOP, for make a treatment decision, for follow-up, and for prophylaxis. Today's gold manometer is the gold standard for pressure measurement, but the cornea must be infinitely thin, must be perfectly elastic, and must be perfectly flexible. We know that the cornea is not an elastic property, it's a viscoelastic property. So we must to find out the biomechanical of the cornea to understand how to measure exactly the pressure. This is what happens when we do standard gold manometer. At the initial stage, there's nothing happen. But at the applanation stage, when the cornea is flat, we have a measure pressure, but the measure pressure is not the true pressure inside the eye, because we have a loading phase. In this phase, the cornea absorbs the pressure, but it's not deformed. This pressure, we call it the PI. And the measure pressure equal PI plus true IOP. If the cornea is stiff, the PI is high, and so the big difference between the measure IOP and the true IOP is different. And if the cornea is soft, the PI is low, and the result is we can believe the result. So to measure the PI, we need to understand the corneal biomechanical property. So the first question, to answer the first question, we need to know the corneal biomechanical property. About the second question, we know that we cannot to measure directly the stiffness of the lamina cryosa. So we need to find out other ocular tissue that has the same property like the sclera, and that's the cornea. Up to now, we have many published many clues to have a strong relationship between the stiffness of cornea and the stiffness of the lamina cryosa. Dr. Mick and Evan showed that both sclera and cornea had a similar collagen content, and the extracellular measures of them is nearly equivalent. Dr. Wu said that the biomechanical characteristics of anterior segment approximated that the whole globe, and Wells in 2008 find that a floppy cornea would be associated with floppy lamina cryosa and peripapillary connective tissue. So if we can measure the stiffness of the cornea, we can have the stiffness of the lamina cryosa. So cornea biomechanical property may be the answer for both important questions above. Let's see how the COVID-ST provides us the cornea biomechanics. Is apply air pressure to the cornea and measure any parameters of the cornea at any stage. We have three main important stages. The first explanation is when the cornea is flat. We call it the first explanation. After that, the cornea is at the highest concavity, and the second explanation is when the cornea is flat again before it returns to original state. At any stage, the COVID-ST machine collects three types of parameters. First is time, second is velocity, and third is amplitude. We call it DCR parameter, dynamic corneal response. Here are some important parameters. At the first explanation, we have A1 length, A1 time, A1 velocity, and A1 deformation amplitude. A1 length is the distance of the cornea at the explanation. A1 time and A1 velocity is the time and the velocity of the cornea when it deforms. And A1 deformation amplitude is the vertical displacement of the cornea. We know that if the cornea is stiff, the A1 length and the A1 time is longer. And the A1 velocity and A1 deformation amplitude is at the highest concavity. We have a big distance. Big distance is the distance in the two peaks of the cornea, and the radius of central concave curvature, the yellow line. We also have the time, and we also have the amplitude concavity. And if the cornea is stiff, the peak distance is shorter, and the radius highest concavity is longer. At that stage, we have important parameters. We call it DA ratio to millimeter. This is the ratio between the red distance and the green distance. If the cornea is short, the red distance is longer, and so this parameters, this index is bigger. And at the A2 explanation, we also have A2 length, A2 time, A2 velocity, and A2 deformation amplitude. This is a very interesting study from China, and they compare the DCR parameter in a asymmetric normal tension glaucoma, and they found that even with equal pressure in both eyes and equal central corneal thickness in both eyes, there has been a significant difference in DCR parameter in a better eye compared to the worst eye. This means that the better eye has a stiffer cornea and maybe a stiffer lamina cryosa, so it's not affected by the glaucoma damage. This is what the COVID-19 machine provides us. They have a big data of population, of normal population, the gray line, and the red line is the value of the patient we are measuring. If the red line is inside the zone of gray line, it's normal, and if it's outside the gray lines, it's abnormal. Yeah. After the machine collect enough parameter, they provide us many important index. As Dr. Sada says above, we have DBI, CBI. In this slide, I just give you three index about glaucoma. That's the BIOB, SBA1, and BCF. What's the BIOB? BIOB is a biomechanical corrected IOB. We know that Goldman thermometers is influenced by, is affected by IOP, by central correctiveness, and by biomechanical property. BIOB, this is the formula of BIOB. They use CCT, they use pressure, they use ACE, and they use highest concavity radius with 19 constant. Any factor, these factors are not affected to the final result of BIOB. So it's independent with ACE, independent with CCT, and independent with corneal biomechanics. And they found that BIOB is more accuracy than Goldman thermometer in patients with corneal surgery and in patients with abnormal corneal biomechanics. This is a very amazing study from Korea, and they compare the pressure from pre-operation and post-operation from a patient and compare the IOP measurement, compare the Goldman tonometer and BIOB tonometer, and they found that in the group of when they use Goldman tonometer, there is a big difference, a significant difference in pre-operation and post-operation. But when they use BIOB, the result is the same. So BIOB may be a best choice for measure the pressure after the corneal surgery. This is a study from Ricardo Vinciguerra. They compare the pressure measured by Goldman tonometer and BIOB from 4 groups: normal person, normal tension patient, high hypertension glaucoma patient, and ocular hypertension patient. And the result is so amazing. In ocular hypertension, there is a big difference between the Goldman tonometer and BIOB. Yeah. In hypertension glaucoma, the result is the same. So it means that in ocular hypertension, we remember the formula. In ocular hypertension, because the cornea is stiff, so it absorbs a lot of pressure, and the PI is very high. So the difference between the measured IOB, the Goldman tonometer, and the true IOB, the BIOB, is so different. Because the cornea is stiff, maybe the laminar granulosa of those patients is stiff too, and it might the optic nerve cannot be damaged by glaucoma disease. In hypertension glaucoma, because the cornea is softer, so the BI is small, and the measured IOB is the same with the true IOB. And because the cornea is soft, the laminar granulosa might be soft too, and it easily to affect by the pressure. So PLB is could help us to separate ocular hypertension at high risk progression to glaucoma from those with only overestimated by standard Goldman tonometer. In clinical practice, when we have a patient with a high IOP, we can use BIOB to decide when to treat or not. The second index is SBA1. SBA1 shows what the stiffness of the cornea. We know that the stiffness of the material is the force applied to that material divide the displacement of the material. With the cornea, the force applied to the cornea is the difference between the air pressure and the true IOP. And the displacement is the deformation amplitude. So the formula of SPA1 is the difference between air pressure and BIOP divide the A1 deflection amplitude, and it shows the stiffness of the cornea. So SPA1 shows us the cornea ability to absorb the pressure, and maybe it shows the lamina crinosa ability to absorb the pressure. If the patient has a stiff cornea, they may have a stiff lamina crinosa, and they have a little, they can absorb the pressure, intraocular pressure, and cannot be damaged by glaucoma disease. This is one study from Dr. Ricardo, and they compare the SBA1 from normal person and normal tension glaucoma, and he see that there is a significant difference in SBA1 between the normal and the normal tension glaucoma. It's very important finding because when in clinical examination, when we have a normal pressure patient with a high risk of glaucoma, we can use SBA1 to separate the patient from normal or normal tension glaucoma. The normal tension glaucoma patient has a very soft cornea, and the normal patient has a stiffer cornea. The last index, the biomechanical glaucoma factor, is a factor based on 5 parameters: DA ratio, highest concavity time, Pachymery slope, BLB, and central corneal thickness. It's a new approach to detecting normal tension glaucoma. This is the formula of BCF. One important study from Dr. Karim Bidunat, he used the BCF to a new factor to discriminate normal eye and normal tension glaucoma eyes. And he found that the BCF showed to be a sensitive and specific to discriminate healthy from normal tension eye with a cut value of 0.5. If the patient have the BCF lower than 0.5, they may be normal. And if the patient has above 0.5, they may be normal tension glaucoma. This is the glaucoma screening software of COVID-19. We see that in the green zone, is the distribution of healthy person, and in the red zone is the distribution of the disease person. And the dark lines is the value of the patient we are measuring. The BCF index in the corner. If it's larger than 0.5, the patient has high risk of glaucoma. To summarize, we have COVID-19 to represent all new ECR parameters relating to corneal biomechanics, and mainly relating to the lamina crinosa stiffness. BIOB is not affected by the age, by CCT, and by biomechanics. SBA1 shows us the ability of cornea to absorb the pressure, and maybe the ability of eyeball wall and lamina crinosa to absorb the intraocular pressure. And BCF is an independent risk factor for normal tension glaucoma and can be used to screen for NTZ patients. Thank you for your attention.
Thank you so much for a very elaborate talk on corneal biomechanics. So I had a very basic question. How much is the average variation in BIOP and Goldman attenuation tonometry you have observed for the same cornea? So does it overestimate or underestimate?
We know that the Goldman tonometers is equal the pressure absorbed to the cornea plus the true IOP. So if the cornea of the patient is soft, it cannot absorb much pressure. So the Goldman equal the IOP. But if the cornea is stiff, it absorbs a lot of pressure. So the difference is significant.
Thank Thank you.
So if you have a Goldman thermometers have a significant difference with the BIOB, the patient has a steep cornea and maybe steep laminar cravation. And
So you base all your diagnosis of glaucoma mainly on BIOP now.
yes,
But you are you also doing a GAT alongside always for the patient or just the BIOP?
If the patient have a high pressure by Goldman thermometer, we treat patient.
Okay.
But if the patient has a relatively normal IOP, we need to use BIOB and SBA1 to separate the patient from normal and normal tension.
Thank you, Dr. Rathi. What is the normal range of vault in the center and the periphery for a scleral lens? Just a very basic question again.
This is a very good question. So the vault, after lens settle after about 4 hours, and then there will be the long-term settlement after months. So after lens settlement, the central vault should be between 200, 150, 200, up to 300, 350. The central vault. Over the limbus, you can have about 75 to 120, and the landing zone, there is no vault because the lens is touching the conjunctival tissue.
Great. So you also mentioned pingiculas and the nodular degenerations, and you customize the lens in those areas as well. Why don't we excise these lesions and then put the lens? Just a thought.
Well, yes, great.
Would it make it more regular and?
You can do both. We have so many technologies now to avoid irritation and between the lens edge and the pinguicula. So you can have a notch, so you can remove a part of the lens periphery. This morning we saw a video how to do this. Okay. So you can do it in your lab. Several labs have some customized technology in lens periphery. They have microvolt or some other the same technology, but the name is different. You can design the same technology with the Wave software. So many technology to solve the same problem. Also, what you can do just to increase the lens diameter. So if the pinguicula is attached to the limbus, you can fit a larger lens and go land on more regular conjunctiva. So you will not have needing any technology there. So you can have regular peripheral zone rather than having microvolts or notches.
Great. So you also mentioned about multifocal lenses in these cases. So I believe these are already keratoconus and very irregular, already have a lot of abrasions. So how do you really, I'm sure it must be very challenging because, fitting a multifocal lens on irregular corneas, very highly abraded eyes must be a challenge.
Yes, multifocal lenses, the multifocal technology.
Are these the patients who want multifocal lenses with
keratoconic patient will never ask for that.
Yes,
because what they want is a good vision
distance
for vision. Okay, for the distance vision. Definitely. If you are adding multifocal optic, it will a little bit compromise the distance vision, and they will not be happy with that. So yeah, you are including some high order aberration also with the multifocal lenses, plus their high order aberration of the eye. It will be not acceptable for them. So for LASIK, post-LASIK, and post-keratoplasty and keratoconic patients, I would not add any multifocal optics.
What is the final amount of high order aberrations you look at? Like that should be your target that can give a good quality of vision to the patient after scleral lenses. So, do you have like a cutoff that your lenses should bring down the aberrations to say a certain range?
Well, this is a great question. So you can reduce high order aberration for about 75% with standard optics. And some patients may be happy with that, some others not. So my reference is not how much I'm reducing, but the patient satisfaction. So I apply the lens and I ask them if they are happy or not, so I can change the technology and increase the reduction of high order aberrations. They are
wonderful. Any more questions? If there are no questions, we would conclude the session. I thank both my co-speakers for their wonderful and very informative talks, and the audience for their participation and attention. Thank you so much, and I would like to thank Mr. Shri for organizing this session for us. It was a very, very informative session, and we all learned great tips. Thank you so much.